would you send us a message?
I'm sorry, Mike doesn't speak Portuguese here.
Okay. Thanks, Álvaro. So we will proceed in English. Okay. All right. We are passing 11. So let's start our webinar. Bruno, I'm gonna do a short introduction and then I will pass you the floor. Okay.
Okay.
And also informing that we are live on YouTube. Hello everyone and welcome to another talk in our webinar series. Today we have Dr. Bruno Morgado from the Observatório Nacional, and Bruno is also a LIneA member. And today he will talk to us about an in-depth view of the Centaur Chariklo and its rings from Stellar Occultations. Before we start, a quick reminder, this webinar is also being streamed live on YouTube. You can find the link on our website or you can access it on our YouTube channel, that is LIneA MCTI. Bruno, thank you very much for being with us today. The floor is yours.
I think Mike is out, so there's anyone here that only speak English? Eu acho que a gente pode ir para português, então. Acho que eu posso apresentar em português, então.
Ok.
Tudo bem?
Acredito que sim. Só checando. Não sei se o Álvaro está com o Mike, se ele só caiu, ele vai voltar.
Caiu, tá, voltou. So, okay. English it is. So, let's go English, that's better. Okay, let me share my screen. Yes. Okay. So, everyone can hear me well. My name is Bruno Morgado, and we'll talk a little bit about Chariklo and its rings as observed by Stellar Occultations. So, okay. So first, let me talk a little bit about myself. I did my graduation in physics here in Brazil in 2009, between 2009 and 2013. I did my master's in the Observatório do Valongo, also here in Rio de Janeiro, between 2013 and 15, and my PhD in the Observatório Nacional. During my PhD, I also had a 1-year stay at Paris Observatory, working in the IMCC together with Valérie LIneA. After I finished my PhD, I did a postdoc in the Paris Observatory. That was a RC LuxStar project. It was between 2019 and 2020. Many of the results that I will present today is about this postdoc in Paris Observatory. And after right now, I am a CNPq postdoc in Observatório Nacional, and I'm working with Dr. Roberto Vieira Martins. I've been working by many years in the astrometry and dynamics of solar system objects. I have a very, I like to work a lot with stellar occultation and also observational techniques. And in a broader sense, I'm very interested in minor bodies and also in the minor bodies of our solar systems. So here is my ORCID and my LinkedIn if you want to look at it. Also, I am a member of the LuxStar team. I'm also a member of the LIneA in the Transneptunian Occultation Network, is the TON. A little bit about LuxStar. LuxStar is a RC project, and it aims to study the small bodies of our solar system, mainly using the technique of the stellar occultations. So this is a collaboration, a very huge collaboration, and it's led by 3 main groups. So there is the Paris group that is led by Bruno Sicardi. The Rio group is led by Roberto Vieira Martins, and the Granada group is led by José Luis Ortiz. And as I said, this is a very global collaboration with observers and researchers all around the globe. So here I have a map containing all the places in the world that already observe a stellar occultation in our network. So this map is not updated. It was less updated in March of 2020, but there's already give us a great idea of how many observers and how huge our collaboration is. Okay, so let me talk a little bit about stellar occultations. So stellar occultations occurs when a solar system crosses in front of a star from an observer on Earth. So we have here the light from a star coming from this direction. The star is very far away, right? So the solar system object will pass in front of this star, causing a shadow here on Earth. So an observer here will see this light curve. This light curve is the flux versus time. And we are seeing here is the light of this star plus the light of the object here in one. And when the occultation occurs, we observe the flux drop. So it goes to almost zero in most cases. So when we observe this kind of thing, we can translate this occultation into a chord in the sky. So here is, for example, so every line of this is a stellar occultation, is an observer on Earth. And here we have a very interesting object. So this is the asteroid Antiope. It was observed in the United States. We have a lot of observers, and it was possible to detect structures and the sizes and shapes with high accuracy. So stellar occultation is a very powerful technique. It allows us not only to probe the object itself, but also the vicinity. So if the object has a ring or a dust shell or an atmosphere, we can detect it using stellar occultations. And for example, in this case, we see that this southern half of Antiope, there's a very strange shape. And this strange shape can be associated with craters of, in this case, contact binary. And so we have a very interesting view of the objects. A byproduct of stellar occultation is also the positions, because we have a very precise position between the body and the star. And right now, the star is known to have a very precise position using Gaia catalog. So we have a very good position of the body itself as well. So in most cases, this good position can allow us to do better predictions and also to really observe next stellar occultations, because we will have a stellar occultation, a good stellar occultation observed. We can measure its position and try to observe next stellar occultations with high accuracy and better results. In some cases, this very good position can also be used to detect non-gravitational force. This was the case for the near-Earth asteroid Apophis, and it was observed in the beginning of this year. Okay, but I'm here most to talk about Chariklo. I will not go into many details about the other objects that we are observing in our collaboration. So let's talk about Chariklo. So Chariklo is a Centaur. It's orbiting the sun around 16 AU. It was discovered in 1907 and is the largest known Centaur. In 2013, a stellar occultation shows us that Chariklo, in fact, has two rings. So we have the C1 and C2 here. And these rings are orbiting around 400 kilometers. This was a very interesting discovery and also explain a lot of the photometric aspects of this object. So this was very interesting at that time. And when we talk about Chariklo and stellar occultations, we have a very stellar occultation help us a lot to understand Chariklo. In 2013, there's the ring discovered, as I said. Between 2014 and 2016, other 12 stellar occultations were observed. This was the work of Diane Berard and Rodrigo Leiber in Paris Observatory. And these positive detections also allow us to improve Chariklo's orbits. And in the beginning of 2017, Chariklo's ephemeris has a precision better than 5 milliards seconds. So we are able to predict stellar occultations that was on point. So we could I forgot the words. We can send stations to observe these occultations and have a very good success. Okay, there are still a lot of questions we want to answer with Chariklo. So the general shapes of the rings, the general shapes of Chariklo itself, the density of this body, also to try to better understand these rings, if there is any inner structure, any details that we want to learn. And all this data can help us understand and help us use dynamical models to better understand the origin and the formation of the system. So try to get these details will help us understand how the Chariklo's rings were formed. And why should we keep doing stellar occultations? Why don't we have to do other techniques or other observations? Here is an image of Hubble Space Telescope, and here we have the Chariklo and its rings. It was just put it here to have an idea. We can see clearly that from the Hubble Space Telescope, we cannot see anything. So we can see details on Chariklo's, we can see details on Chariklo, we can see Chariklo's rings because the PSF of Hubble is about 30 mass. 30 mass at Chariklo distance is about 300 kilometers. So it's a lot. It's impossible to detect the rings using Hubble Space Telescope. Also, the sphere, that's an instrument with adaptive optics, also have a PSF around 30 mass or 40 mass. So also we cannot obtain data on Chariklo rings using these instruments. On the other hand, here we have an stellar occultation observed in Namibia. It was in April 2017. This is a kind of a spoiler, but just to show you a little bit. We have very small telescopes, around 30 and 50 centimeters. The exposure time was about 0.1 seconds. And we can see that we detect Chariklo rings, and also we detect structures within the Chariklo's rings. That's so we have very details. We have a lot of information about the rings itself that can be used to determine, to better understand the system. So in this case, the spatial resolution was about 0.5 kilometers per data point. So we have a very high spatial resolution. So this really give us a lot of information. Okay, so let me talk a little bit about observations. So this is the stellar occultation observed in 2017 July. When we try to do stellar occultations, we need to do a lot of things before the stellar occultation itself. So we have to predict the event. And when we predict the event, we can also have to do some last-minute astrometry to better improve these predictions and really pinpoint the location of the shadow on Earth. For many large telescopes, we have to request time. So this is the case for OPD, for SOAR, Danish, and many large telescopes. In case of the amateur community, we have to mobilize them. We have to send emails and contact them and keep in touch to motivate them to observe this stellar occultation with us. In some cases, we still have to deploy stations. So here, for example, we have one observer in Guaratinguetá that grabbed a camera and went to São José do Rio Preto. And also here in Argentina, we have some observers that get the telescopes and the cameras and went to observe in another place to get a better data. Of course, after all the occultation, we have to get all this data and all this reports. For this occultation here, we have something was about, if I remember correctly, it was about 300 gigabytes of data, the resulted data from this campaign. And here's just the color bar for each point, so we don't have to go into details about this, but we have a lot of data, a lot of observers, a lot of organization issues that we have to attempt and to have to be sure to be able to get a good results on this observation, on this stellar occultations and in this all this process, right? Okay. After we have the data, we have to analyze it. I will just go very quickly on the analysis procedure in the pipeline that we use. So from the observation, we usually have the images. In some cases, we don't have images. We have something like a video, an AVI file. So when we have this, we have to convert the video file to a FITS file. This was usually done using Tangra, or a Python software that I developed to use this. So after we have the fits, when we have some calibration, so such as bias or flat field, we use the calibration. This calibration was done using IREF or PyRef. After the calibration, we do a photometry. So we have to measure the flux of the star in each image. And for most cases, we use the prior package to do that. This is a package developed by Marcelo Assafin. And after that, we have the light curve. So this is a result by itself. The light curve is something that we store, and we have this information, right? So after we have the light curve, we determine the timings, so the disappearance and reappearance time of the star. We can also do the projection of these times in the sky plane. So we have 2 points, F and G. And of course, when we are treating about ring detections, we can also project it in the ring plane and get some ring local parameters. To do the timing, we have to use a lot of information, such as the ephemeris, the star catalog, and create some models. We then have our chords, and we try to fit the limb, so to determine the size and shape of the objects. For most of the parts here about about timing and the projections and the lib fitting, I've been using Sora. Is a package that was developed by Altair Gomes Jr. and myself, Bruno Morgado, in collaboration with many other people, such as Rodrigo, Guga, and others. And here is the website of our Python package. Okay, so let's go to the results. There is a lot of results that I have to show you today about rings and its system. So if anything is a little bit confused, please just send me a question. I'm always available to answer. So the first thing we are fitting the ring radius and the pole position. So considering the first ring, the C1 ring. For this, we are fitting an ellipse and the projected ring times, and we are trying to get our 5 parameters. So there is the center of the rings, the oblateness, the same major axis, and the position angle. Here, we are considering that the rings are circular, so all oblateness is due to geometry. So we can compute the pole position considering these parameters. So the results we are obtaining here, so we have 2 stellar occultations in 2017 that allow us to do this kind of analysis, because we have a number of chords that allow us to get the global shape of the ring. And here we are comparing the pole position in declination and right ascension, also with the discovery position that was observed in 2013. One thing that is interesting here is that we don't have a difference between the pole position detected in the different occultations. All of them are in the same 1 sigma value. So this can give us an information that the ring didn't change between 2013 to 2017. It's a global aspect, of course. So this is very interesting because we cannot discard the possibility of Chariklo rings to be circular, because if the ring's eccentricity is large enough, we will have to detect something here, some difference from the expected values between the occultations. Okay, so before I was talking about global parameters, and now I'm going to details on the rings. So we're looking about structures in the ring. So for it, first I have to show you something. So for this, we have to consider only the resolved detections, because the resolved detections of the ring will allow us to fit the immersion and immersion time, and also the opacity of this ring. And this can be a problem when we don't have a resolved detection. A resolved detection is when we have more than a quantity, more than some numbers of points within the detections. So here I have the detections of the observation of TRAPPIST, is TRAPPIST South in reality. So the exposure time was about 2 seconds. And here we have the light curve. The red stripes are the exposure time. So this information here is for all of this region. Interesting, because this light curve can be represented by something like this. So this in blue is the model. So this is a model that can represent this data point. But this is also a model that can represent this data point, because as we don't know exactly we cannot differentiate between these two models, and that's really the point. In reality, the real occultation was like this. This was an observation by Danish in the same station. This is LIneA. So here is the observation by Danish, and here's the observation by TRAPPIST. So everything seems to, their combination can give this information, but the TRAPPIST itself cannot allow us to have major information about Chariklo's rings. However, the Danish data can help us improve and help us understand the rings. So when we have a resolved detection, we can determine the radial width of the ring, first in the sky plane and then projected in the ring plane. And we can see something like this. So this is the stellar occultation that I showed before in April 2017. And here we have the flux over radial distance in the ring plane. So here is the detections of the rings. So as I said before, we can see structures in the rings. And more important, these structures are consistent for different observations. So different observations, so different observers, different places on Earth, different instrumentations also shows a similar feature of the ring. So this is not noise, right? It's really a detection. Here I have the case for the stellar occultation that I showed before with here in South America in July 2017 with many observations. And we have here VLT, here we have here Danish telescopes, I have here the OPD telescope, and we see these structures in the rings, and these structures are consistent in the different observations. So that's very interesting. Just one comment about the 5 here. This is Tololo. So we have prompt and SARA data. And this occultation was a very interesting one because, in fact, there was grazing. So the light curve never left the ring, never goes on the other side of the ring, just crossing the ring here, grazing. So that's why the point here never goes up again. They are just go down here and go up in the other side of the ring. So this is all the structures and rings that we have since 2014. So we can see that the ring here are sorted by radial widths. So one thing that is interesting, there is a significant difference in radial widths for the ring over all the detections. So the width of the ring changes with time, or also changes with position in the occultation position at the moment. And this is a very interesting thing because, as I said before, it gives information about how the physical parameters of these rings. When we put here a plot considering the radial width over the detection number, we see that there's a large difference. So the mean value was about 7 kilometers. We have a maximum value of 9.1 and a minimum value of 4.8 kilometers. And with these values, we can try to compute the eccentricity of the ring if we do some assumptions. And when we do these assumptions, and these assumptions are that the ring is has a mode m equals 1, we have the eccentricity of this ring should be higher than 0.005. So this is, we're trying to get some informations about the eccentricity of Chariklo rings. Okay, during this occultation in 2017, in July, we also have a very special data. So this was the data of the Danish telescope. This occultation was observed by 2 filters in the same telescope, in the same instrumentation. And it was this visual and this red band here. And just to show it, this is the transmission over the wavelength. And just to comparison, this is the wavelength. Sorry, just a second. And just to comparison, here's the wavelengths of this, of some of the Johnson's filters, and here's the Sloan filters. Okay, so when we see together the light curves from the Danish telescopes, we have here in red the red filter and in green the visual band. And what we see, there is no difference in these 2 data sets. And that includes this W-shaped structure. So that's very interesting because this can give us hints about the particles of the ring. If the particles of the rings are in the same length as the wavelengths, there should be a difference between these 2 bands. We should have seen a difference. But in fact, what this is showing us that the ring particles should be larger than this wavelength. In fact, the ring particles should be larger than 1 micron. This is already expected. The ring particle is expected to be something like centimeters if we consider the analog rings of Uranus and some Saturnian rings. So this is nothing very new, but this is an observational constraint showing that the ring should be larger, the ring particle should be larger than 1 micron. Okay, so in this part, some of the conclusions are, we have very clear detections of these W-shaped structures. So we're having many detections of it, so it's real. We have a variation in the radial width of the ring. This can also indicate some eccentricity of the rings. And there is no difference between the observation in the 2 filters, meaning a particle size larger than 1 micron. Okay, so now going to the C2, C2 is a very narrow ring. So here is the detection of C1, and here is the detection of C2. So we can see that's a very, in most cases, are 1 point detection because the ring is very narrow. So we cannot be able to really detect the width of the ring. What we can do is estimate the equivalent width, that is the width times the opacity. So for C2, we have something around 100 meters of equivalent width. But with these 6 detections here, we are able to fit an ellipse and try to see how this data compares with the first ring, the C1 ring. And one thing that is very interesting is that the global shape of the rings are similar. The pole position is exactly the same, is almost exactly the same within 1 sigma. However, the center of the ring has a little bit a discrepancy. There's a little bit difference between the center of the 2 rings. This can also show us an eccentricity, a differential eccentricity between the 2 rings. So this is a very interesting thing. However, it's important to say that this difference is within a 3 sigma confidence level. So we cannot say for sure there is a difference, but there is we may argue that this difference is real, but we have to take this information with caution. And here I'm showing the difference of radii between the 2 rings, considering the best fitted ellipse and all the ellipses within the 1 sigma. So this is the difference between the 2 rings, the radial difference. So the space between the 2 rings varies around 19 kilometers, with a maximum of 19 kilometers and a minimum of 10 kilometers. So we have a variation between the 2 rings. About this part, we can conclude that there's a 1 sigma agreement between the pole position of the 2 rings and less than 3 sigma agreements between the center position. But as I said, as this is not a 1 sigma agreement, this should be considered with caution. We not determine the width of this rings, but we can determine the equivalent width, and has this value here. And also the global radial difference between the rings was about this value, ranging between 10 and 20 kilometers. Okay, now going to the 3D size and shape of Chariklo. I think I still have something like 10 to 15 minutes, right, Rodrigo?
Yes, you're good to go.
Okay, so let's talk about the 3D model of Chariklo. Now, as we have multiple detections of Chariklo, I will try to fit the same 3D model in all the occultations. So the idea is I have to do some assumptions. So the assumptions are the pole position is constant between for this interval of time, so between 2013 until 2020. Also, the main body of the Chariklo center is the same as the Chariklo's ring center. This is a first approximation. Then after some steps, we will go back to this to try to check if this is true. I'm considering that the rotational period of Chariklo is known, and this is the value as provided us by Fornazier et al. In 2014. I'm considering the Chariklos a triaxial ellipsoid, and here is some just information here. And I will do, to fit this, I will do a Monte Carlo. So my initial guess is this A, B, and C values varying in this range. My omega 0 is just the angle in the reference epoch, should be vary between 0 and 260. And this is just the period that I showed before. These are the occultation that I'm considering. The one with the star was first presented in this work. Before, we have some occultations that was observed and published by Rodrigo Leiva and Jan Berra. Most of this process was done in the Santos Dumont supercomputer at LNCC, thanks to LIneA and the LIneA collaboration. So this is the best fit we have. So this is the 3D model that we fit to the chords and all the chords. So this is the value, and the residual was around 4 kilometers. And this is also an idea of topography features in Chariklo. So probably the topography of Chariklo is around this value, about 4 to 5 kilometers. And this is the best value that we found for the triaxial ellipsoid. One thing that we can do is to check if this triaxial ellipsoid is consistent with the literature. So we get the variational magnitude from light curves, so rotational light curves, and check if our model are consistent with these values. Of course, there's some difference that can have some topographic features, some albedo variations. So our model is not perfect, and that's okay, but it should give us a very good hint and shows a very good agreement. And in fact, it's true, and it shows us that. Here are the observations, and here are the variations of our model. So our model fits quite well with the observational data. For this, I'm not considering the C2, but that's okay because C2 is faint and will not change much this information here. Also, I can check the Chariklo's density. So we don't know Chariklo's mass, so that's a problem. Different from LIneA, that we have a satellite, and we have LIneA's mass very good. We have a very good detection of LIneA mass. We don't have that for Chariklo, so we cannot say for sure the mass of Chariklo. So we can do some considerations. One of the most usual consideration is the hydrostatic equilibrium. So usually an object will have some shapes. The 3D ellipsoidal shape should be a Jacobi ellipsoid. And when we know the rotational period, we can compare these values and see if, in fact, this ellipsoid here is the same as can be considered a Jacobi ellipsoid. And the answer that we found is no. Chariklo is not consistent with a Jacobi ellipsoid. Jacobi ellipsoid should have an omega between 0.284 and 0.374. And in fact, of the value that we found is about 0.191. So we cannot consider Chariklo as a body in hydrostatic equilibrium with the Jacobi equilibrium figure. This is still something that we need to understand better, why Chariklo don't have the Jacobi ellipsoid figure. Possible there is some mass variation or some other structures there that we still need to understand better. Okay, so here, considering the Chariklo 3D shape and size, we can see that Chariklo is consistent with a triaxial ellipsoid. We have a very good fit, considering all the occultations. So the residual suggests topographic features around 3 to 4 kilometers. And the ellipsoidal shape that we found is consistent with the light curves observed by Chariklo, but is not consistent with the Jacobi equilibrium figure. So there's still a lot of things that we still need to answer about this object. Okay, so After we fit the 3D body of Chariklo and also the rings, it's interesting to check the center position between the ring and the main body to see if we can detect some eccentricity of the rings, some variation in the center. And what we have here is that we cannot detect any eccentricity. However, we can detect some higher limits of eccentricity. Some higher limits. So in fact, the C1 ring cannot have an eccentricity larger than 0.022. This is considering a 3 sigma, or a 0.014 considering a 1 sigma value. Here we have the black, the blue, and the green. The dark colors are the 1 sigma, and the light colors are the 3 sigma. So what I'm looking here is the maximum difference between one value here to one value here. So let's, for example, use the main body and the C2, and the maximum distance will be something like here, right? And this maximum difference is about 3 kilometers, and 6 and 7 kilometers if we consider the 3 sigma, and that is where this value comes from. So we are able to see that Chariklo eccentricity should be less than these values here. Okay. And as I said before, also from stellar occultations, there is a byproduct. There is the astrometrical position. So we did the astrometry of these occultations and get very precise astrometry. In fact, this astrometry is usually below 1 mass. So we have a very high astrometry. Usually, when we do the astrometry from an image, you go to the telescope, point to the object, and do the astrometry, we have values ranging between 10 to 20 mass. So stellar occultations is smaller, very, very smaller than this value. And when we see the orbits of these objects, so here is a comparison between the NIMA orbit and the GPL's orbit for Chariklo. So here's the difference in rate ascension, here the difference in declination over time. All the yellow points here are stellar occultations and the values that we obtain in this project. And we can see that the orbit has a very small uncertainty. I don't know if you can see it, but there is a black line here, and that's a gray zone. I think you can see something here and here. And this gray zone is the uncertainty of the ephemeris. So in fact, we have very precise ephemeris for Chariklo. When we see the values for 2022 in January, we have an uncertainty of around 2 mass, that is about 20 kilometers. And for 2033, we have something like 3 mass, so 30 kilometers. So even in 2024, we will still have very precise astrometry, and we can do very precise occultation predictions and hopefully observe more occultations and get more information and more data. And to conclude, so Chariklo has been observed by stellar occultations since 2013. We have many stellar occultations since then, and we are able to detect CR1, C2, and also the Chariklo main body. And during this project was the first time that we did it with multiple detections. So that's very interesting, and that's the main point of this project. Also, all the values that I show here can be used to constrain the dynamical models and can help us understand this system. So here, just to show you how the stellar occultations and the publications that we have. Okay, so the takeaway message during this project, we are able to get the global shape parameters of the first ring, C1. We also were able to detect structures, local structures in the C1 ring, so these W-shaped structures here. We are able to detect the global shape of the C2 ring for the first time, and also have a 3D shape for Chariklo. All this work is presented in this paper here that is available in the archive and also in the ANA, Astronomy and Astrophysics. Here is the paper. And it was just accepted a month ago and is online, public in the forthcoming papers. And that's it. Thank you, everyone.
Okay. Thank you, Bruno, for the remarkably interesting talk. We now have time for some questions. If you joined us on YouTube, you can put your question in the comment section and I will redirect it to Bruno. And if you joined us in Zoom, please raise your hand and you can ask the question yourself. So, questions? Okay, Adriano, please go ahead.
Hi, Bruno. Thank you for the presentation. Do you have an idea about what is causing the gap into the C1 ring? Some kind of resonance or anything like this?
That's exactly what we still want to understand. You are saying about the W structure or about the gap between both rings? The gap between both rings will probably be is caused by a satellite, a shepherd satellite, but we never detect the satellite. It's just a speculation. And the gap is probably something like related to resonance, but we still don't know. The dynamic of the system is still a lot of things that we don't know about it. That's why we need this kind of projects that have observational data that can be used to constrain the dynamical models.
Okay, thank you.
Thank you, Adriano. So, more questions? Márcio, go ahead.
Ok. Eu não tenho uma pergunta científica a fazer, mas o que eu gostaria é de salientar o esforço que foi feito por um grupo de pesquisadores aqui do Brasil, que se colocou internacionalmente em colaboração com grupos importantes, conseguiram adicionar a isso a contribuição da ciência cidadã vinda de astrônomos amadores. Eu acho que cada vez mais isso está sendo valorizado e o próprio Brasil está começando a ter esse pessoal mais preparado para uma colaboração. Então, eu acho que os resultados científicos obtidos até o momento, e os que ainda virão, porque as perspectivas são boas, ainda mais num contexto moedor de carne que vem se encontrando a ciência brasileira nos últimos 10 a 15 anos, e, em particular, nos últimos 4, 5. Então, é um feito absolutamente meritório e que sirva de exemplo de que é possível se trabalhar, mesmo nadando contra uma corrente aí de alta velocidade. Alguma hora, essa água rápida vai ter que acabar e vocês vão estar preparados para nadar muito mais rápido a favor da corrente. Então, eu deixo ao grupo todo meus parabéns por esse trabalho fantástico, que hoje foi resumido algo do tipo 10 a 15 anos de atividade observacional, teórica, de interpretação, de redução. Quando vocês veem todo o pipeline que envolve até chegar no resultado científico, é algo sensacional, envolvendo um grupo, porque atividades individuais, às vezes pode ter um despontando aqui, outro lá, mas ter um grupo sério trabalhando, só deixo aí meus parabéns. Gente, que continue desse jeito aí. Um abraço.
Thanks, Márcio.
Obrigado, Márcio. Okay. More questions, comments? Bruno, do you have any expectations for new observations or data collection for these studies? Will we have like occultations this year or next year?
For Chariklo, in fact, there's a problem because we don't have any future occultation that will be very, very good, because the collaboration now is huge, mostly in the Europe, North America, and a little bit here in South America as well. And when we have an stellar occultation passing by these regions, we can do a lot of very interesting things. But in fact, for Chariklo, we don't have this luck. For the next, I think, couple of years, we will have some interesting events, but it's it's not that good comparing with others. Because, for instance, I think it was last year, we have a very huge campaign in Europe for 2002 MS4, is a TNO. So we had more than hundreds observations. So we are able to really pinpoint and have a lot of information about these objects. Unfortunately, we don't have an event passing by Europa using an event by Chariklo passing by Europa. It would be very, very interesting.
Yeah, that's a pity. Thanks. Adriano, do you have another question?
One more question regarding the possible satellites. Do you have an upper limit for the size of the possible satellites of Chariklo?
I don't have this number by heart, but it would be usually 1 kilometer or less if we compare with some Saturnian satellites. I'm not completely sure about this number I'm saying, but will be something like this. So okay. It will be a very, very small object.
Yeah, just to have an idea of the size, possible size. Thanks.
Guga put some words in the chat. From the Hubble Space Telescope images, we have a limit of 1 kilometer.
Thanks, Guga.
Okay. We still have a few minutes for questions.
Okay, may I ask one?
Sure, go ahead.
Is Chariklo special, or we may expect rings on other bodies, like for LIneA, but in a body at the size of Chariklo, or smaller, let's say?
Yeah, that's a very interesting question, and this is something that we still want to learn. And that's why we are doing stellar occultation by many objects, because we can always find something interesting in the next object. We have these rings around LIneA, and LIneA is larger than Chariklo. We have a possible ring around Chiron that's also was detected some structures around Chiron, but as far as I know, we are never able to really say that it was a ring. Mostly because we didn't have any stellar occultation with very good data precision, with very good data and this kind of precision. However, I think we should keep observing many objects and trying to search for rings and for the unexpected. Only a dynamical study will show why if Chariklo is special or not. Why there is a ring? We don't know why there is a ring there. In the sense, we don't know the mechanism that can be keeping the ring there. So there is still a lot of things that we don't know and we want to know. So in my opinion, Chariklo is not special, but let's see.
You are muted, Rodrigo.
Oh, sorry. Thanks. I didn't understand. Flavia, did you have a question?
No, I just was warning.
Okay, thank you. So we have time for a last question. Okay, well, if there are no more questions, we will now wrap this up. This presentation will be available on our website and on LIneA's YouTube channel. And for the next week's webinar, we will have Hugo Camacho from São Paulo State University. He will be giving us an overview about the cosmological results from the first 3 years of observations of the dark energy survey. Thank you, everyone. And a special thanks to Bruno. Obrigado, Bruno.
De nada. Tchau, tchau.
Okay, everyone have a great day. Stay safe, and I hope to see you all next week again. Bye-bye. Ciao, ciao.
Bye-bye.
Bye-bye.